Welcome to the Python Programming tutorial series for Climate Mathematics Theory and Applications. In this video, we will continue to cover Chapter 3, Basic Statistical Methods, but focusing on confidence intervals and statistical inference. Let's begin with looking at confidence intervals on global temperature data, namely our NOAA global temp data from 1880 to 2015. You can find this data at the highlighted URL. In order to upload this data into Python, we are going to be using the pandas module, accessing the read table function. We do indicate that this file does not have a header, but it does have white spaces as its delimiter, ensuring that we're reading in this file correctly. I'm going to access the values of that file with our .values method. Then I will be taking the second column only and be naming it tmean15. I'm going to have a mean estimate, which is just going to be the mean of our tmean15 and our standard deviation of that tmean15 variable. Next, I will be calculating the standard error, which can be calculated from your standard deviation divided by the square root of your sample size. Then we are going to have our error variable, which is going to be computed with 1.96 times your standard error. We are going to get all of these items printed in a nice print statement. We have our mean estimate as seen in the highlighted text. We have our lower bound seen in the highlighted text, and our upper bound seen in the highlighted text. We found these upper and lower bounds from subtracting our error from our mean estimate and adding our error from our mean estimate. We will now be going into statistical inference for x bar, so our sample mean, using a z-score. First, let us set mu and sigma, namely mu equals 0, sigma equals 1. We're just going to reiterate that normal probability function with the definition of int g. We are going to be using this integrating function again. This time we are going to be using a little bit different desired quantities. We have a underscore and b underscore equaling to -3 and -2.4 respectively, and then a and b variables equaling to -1.96 and 3 respectively. We're going to let x equal that numpy line space from -3 to 3. Then we are going to let y equal the integral on that x variable. Next, we're going to be creating our figure. We have our fig and our x variables equaling to our subplots method, which is creating that figure for us internally. Then we are going to be plotting x and y in black with a line width of 1 on our figure. We're going to once again set that y limit equaling to the bottom equals 0. Now we're going to go into making our shaded regions. We do need some uniformly distributed sequences. ix underscore and ix will be those sequences that we need to integrate on our appropriate values. Next, we are going to be plugging in that ix underscore into our int function, and we are going to name it iy underscore. We're going to do the same thing with the ix variable, plugging it into the int g function and naming the result iy. Next, we have to create that vertical separation so we can see the differences between these quantities. So we have verts underscore defined here and verts defined here. Next, I will be creating the shaded polygons that we are going to be adding to our plot. We have poly underscore and poly created in very similar ways. We're going to be using that polygon function that we imported at the beginning of the video. We're going to be using that polygon function on verts underscore with a face color of light blue. And we are going to be using our verts as parameter in our polygon function with a face color that is pound A4 C94A4. You can use English colors, but you can also use RGBA colors and hex colors in any color parameter in Python. Next, we are going to be adding the patches that we just created using that add patch method on our poly underscore and our regular poly variables. So our plot does have these polygons on it. We're going to be adding our text with that height and that width position parameters, followed by our text and some other centering parameters. We're going to be creating another arrow to be displaying on our plot with a dictated text named p-value. So on the plot, when you see p-value, the arrow that it is pointing to can be made using these dimensions. We are going to label our plot with a Y label, an X label, and a title. We are going to be setting our Y limits from 0 to 0.5. Next, we are going to be setting various parameters. We do want our X ticks to pop up. We are going to be having X ticks from B underscore to A. Then we are going to be setting those tick labels as the following. We have a Z and we have Z underscore 0.025. These two labels will show up in the positions of these two parameters. Next, I'm just going to add a little bit of extra text as seen in the highlighted text. We're going to be setting our Y ticks to nothing and setting our Y labels to nothing. This AXV line will add a vertical line at our desired quantity to our plot. We're going to have our vertical line where X is equal to negative 1.96. This line is going to have a color of red. Lastly, we are going to add some arrows to our plot to indicate certain types of regions. We will be adding a light blue arrow to indicate our H1 region, which is our alternative hypothesis. We will also be adding a light green arrow indicated with that hex number to indicate our HO region, which is our null hypothesis region. We are going to wrap this whole block of code in a PLT show, and we do get this beautiful z-score, p-value, and significance level plot to show. We can see that we have a lot of arrows going on based off of the arrows that we used. We have our H1 region on the left side of our red vertical line, and our HO region in green on the right side of that red vertical line. We can see that our p-value does have an arrow pointing to this blue region on it. The blue region can be found by looking at your z-score. The red line that we added to our plot lines up with z of 0.025, which is a negative 1.96 z-score. With this z-score, we do have an HO probability of 0.97 indicated in the green region on our plot. Next, we will be going into finding mean of a small sample size using a t-test. We're going to be using hypothesis testing on the NOAA global temperature values between 2006 and 2015. We're going to have to import our data. This data can be found using the highlighted URL. We're going to import this data using our pandas module with that read table function. We're going to grab our values. We are going to grab our desired values, which is just the values from 2006 to 2015, which is indicated with this slice. We're going to be setting our mean of our sample and our standard deviation of our sample. Our sample size is going to have a sample size of 10. Then we are going to be calculating our t-score manually using the mean estimate minus 0 divided by the standard deviation divided by the square root of our sample size. This does give us a t-score, which we can print out in the following print statement. Our sample has a mean seen in the highlighted text. Our sample has a standard deviation seen in the highlighted text. And our sample returned a t-score of negative 20.47. This is quite a huge t-score. So this can lead us to believe that we would reject this hypothesis testing, meaning that our mean is not truly equal to 0. We can verify this t-score with a p-value. We are going to be using our t module with our PDF function on the desired t-score with degrees of freedom equaling to n-1. According to this function, we do get a p-value of 1.598 e to the negative 9. This is approximately 0. We do retrieve a very, very small decimal from having that t-score of negative 20. In order to yield your critical t-score, meaning we would reject any t-score larger in absolute value from the score obtained in the following statement. We could go ahead and use the t module accessing the ppf function. If we wanted a 0.975 confidence limit on our t-score, we are going to use 1 minus 0.025 as our first parameter, followed by our degrees of freedom, which is n minus 1. We do retrieve a critical t-score of about 2.26, indicating that we do have statistical evidence to reject the null hypothesis of this test. Next, we are going to be comparing temperatures of two short periods. We are going to be hypothesis testing for global temp from 1981 to 1990 and comparing it to the global temp between 1991 and 2000. You can access this data in the highlighted URL. We are going to name this data DAT1, and then we are going to rename DAT1 with the values that we collect from this data. We're next going to separate it into two sets. TM 81 to 90 is going to be our global temperature data from 1981 to 1990, indicated with this slice. TM 9100 can be found in the highlighted text. This will include the global temperature data from 1991 to 2000, indicated with this row slice. We're going to find the mean of each data and name it bar T1 and bar T2. We are also going to be finding the standard deviation of each of our samples, S1 SD and S2 SD. Next, we're going to be setting the sample sizes of both of those, making N1 equal N2, which equals 10. Next, we are going to define the variable spool equaling to the square root of N1 minus 1 times the standard deviation of our first sample squared plus N2 minus 1 times the sample standard deviation of our second sample squared divided by N1 plus N2 minus 2. In order to yield the t-score and boundary conditions for the critical value, we will be computing the following. We will be naming t equaling to our mean of our sample minus the mean of our other sample. We're going to be dividing this difference by the spool times our square root of 1 divided by N1 plus 1 divided by N2. This arithmetic right here will yield a t-score for a two-sample hypothesis test. We're going to find our lower and upper bounds using the ppf function that we used previously. Our lower bound is going to start at 0.025 with degrees of freedom equaling to N1 plus N2 minus 2. Our upper boundary condition could be found by using 1 minus 0.025 with the same degrees of freedom as listed above. Next, we can print our t-score and our t lower bound and upper bound, which produces a t-score of negative 15.95. We have a lower bound on our t critical value as negative 2.1 and an upper critical value of 2.1. This provides us some insight that we might reject our null hypothesis. If we wanted to find our p-value that corresponds with the highlighted t-score, we could go ahead and use that t.pdf method on our t-score with our degrees of freedom, which it does render a p-value of 2.42 e to the negative 12, meaning that we do have statistical evidence to reject our null hypothesis. If we wanted to print the means of the separated data, we can just do that in a print statement, labeling what each of them are. We do have a mean of negative 0.286 for our data between 1981 and 1990, and a mean value of negative 0.425 for our global temperature data from 1991 to 2000. The difference between these two means is negative 0.1389. Lastly, we are going to be using some statistical inference on a linear trend. We're going to be using the same data that we've been working with. You can upload this data from the URL that is highlighted. Just a reminder that this file does not have headers and its delimiter is white spaces. We're going to be grabbing those values. Then we are going to be grabbing all rows but only our second column of data. We're going to be creating a uniform time sequence using that line space function in the NumPy module. Next, we will be creating our linear regression and naming it LM. We are going to fit our linear regression model with our time sequence and our data that we grabbed from the highlighted URL. We are going to be using the time sequence to predict the global temperature data that we are looking for. We are going to make some predictions off of this LM fitted model that we just created using that predict method. We're going to be predicting the global temperature values for the time O sequence that we created above. Next, we are just going to print some important information that could be found in our model. Namely, the coefficient of our model is quite small, being at a value of 0.0069. The intercept of our linear model being at a value of negative 13.79. But most importantly, the R squared of our model is 0.68, indicating that our model can predict roughly 68% of the variance that is shown in our global temperature data. This concludes Chapter 3, Basic Statistical Methods of the Python Programming Series for Climate Mathematics, Theory, and Applications. Join us next time for Chapter 4, Climate Data, Matrices, and Linear Algebra.